Okay, let's go through this exam, hopefully quickly. All right, so we will begin it, and I'm going to go ahead and do it the same way I would have expected you to do it, not using a compiler or anything. So that leaves room for, missing curly brace or whatever, that kind of stuff. All right, question 1. Why are arrays considered fast and memory efficient, while linked lists are slow and memory efficient? All right, so arrays are stored in contiguous memory and therefore must block off all of the memory that will be used for the array at the beginning, which is memory inefficient. While linked lists only generate memory when a new element is created, and that memory does not need to be next to the previous element in memory. This is memory efficient. Since arrays are stored in contiguous memory, individual elements can be accessed directly using a base address and an offset to immediately get to the bucket you want. While linked lists require that you traverse the list element by element to the place you want. Something along those lines. All right, create a class for representing student objects. A student has a name, email, and GPA. Make sure to include all necessary constructors and getters and setters. You could have made the header file for this if you wanted to, but you didn't have to. But if you wanted to, the header file would look something like this. Class student. And let's see, is a name, email, and GPA. So we'll say string name. Well, we have a private section. String name, string email, maybe double GPA, something like that. You would have had to do the, include namespace. Standard. I didn't care if you did that kind of stuff. That would give you access to the string thing. I was mostly looking for competence. And then we want to have a constructor. So we'll have a student constructor that'll take in a string name, a string email, double GPA. And then we want the getters and setters. Now you actually could implement the whole thing in a single file, but I'll go ahead and, so this is going to be what is called student.hpp. So we're going to say string get name, string get email, double get GPA, void set name, set email. And these should take strings as parameters. Set GPA, something like that. All right, so let's say that's the end of that file, and then this is going to be student.cpp. So we'll do an include student.hpp. And then we're going to go ahead and implement all these things. It's going to be students : Let's go ahead and fill those all in here. Right, and this name is equal to name. This email is equal to email. This GPA is equal to GPA. That's our constructor. Get name. Return this dot name. Get email. Return this email. Get GPA. Return this GPA. Set name. This name is equal to name. Set email. This email is equal to email. Set GPA. Oh. This GPA is equal to GPA. All right, so something along those lines. If you didn't create the header file and you just created this CPP thing down here, I was okay with that. I just wanted to see that you understood how to create a class that had fields and a constructor and some getters and setters. So as long as you showed me competence in that, it was fine. All right, this guy from binary to hex. So this is using our shortcut. So you can split this into two things. So this is 1s, 2s, 4s, 8s. So this is 12, 13. So that what's that, D, right? A, B, C, D, yep. And then this is 12. Which is a C. So our answer is DC. Okay. Write a method that takes an array of ints as a parameter, reverses that array in place. That is to say that your method does not return a value, but rather updates the existing array to be the reverse of itself. Okay. So return nothing, reverse array. We'll take a array AR as a parameter like that. All right, I'm going to go ahead and create a temp array. And this guy is going to be the size of AR. And if you made up a method called length for your array, that's okay. Remember we talked about that new style arrays, size of will give you the length, but they're actually stored as primitive types, not objects. But you know, getting the size of your array, I don't necessarily care how you accomplish that, as long as it was something reasonable. So what I'm going to go ahead is I'm going to walk this array in reverse and fill up this other array. So I'll say int pause is equal to 0, or int I is equal to size of AR minus 1, which is the last legal bucket, as long as it's greater than 0. I minus minus. And then I'll say temp at bucket pause is equal to AR at bucket I. Make sure I do pause plus plus. So that copies it in reverse. Now I just need to copy it back. I is equal to 0. I is less than size of, doesn't matter if I choose AR or temp. We'll say AR at bucket I is equal to temp at bucket I. All right, so what we did is we went through AR in reverse, setting temp forward, starting at bucket 0 with those elements backwards. So temp ends up being a copy of AR in reverse. Then I just went through and copied the contents of temp directly over to AR, which then overwrites the original memory of AR with temp in reverse. Okay, assuming you have access to a linked list of ints, class similar to what we wrote in class, write a method that takes a linked list as a parameter and removes all odd numbers from that list. You may assume that you have access to the following methods: add front, add end, add index, remove front, remove end, yada, yada, yada. Okay. So write a method. Okay, so this is going to be called void. What do I do? Removing odds. I'll take a linked list as a parameter. What I'm going to do is I'm going to go ahead and create a linked list pointer temp as an empty linked list, because if you start removing elements, actually, you know what? I'm going to do it this way. So we have two ways of doing it. So I'm going to say that if you start removing elements from a linked list, what you've actually done is you have changed the size of that linked list. You know what? Yeah, I'm going to do it, I think, the way that you probably did it, which means that you then need to adjust the count. So I'm going to say for int I is equal to 0, I is less than LL get count I plus plus. Then we're going to ask the question if LL get at index I mod 2 is equal to 1. If it's an odd number, then what do I want to do with it? Well, if it's an odd number, I want to remove it. So I'll say LL remove at index. That is what I'm doing, removing odds, right? Remove all odd numbers. So I'll remove at index I. So now what I just did, though, is I shrunk the size of my linked list. So by doing that, I actually now need to artificially reduce the value of I by 1. Because what I just did is, let's say I just removed bucket 2. Well, if I just remove bucket 2, then the next guy is going to be the new. Oh, actually, I'm sorry. I need to increment by 1 so that the, oh, no, I had it right. So I'm going to decrement by 1, because if I just remove bucket 2, that means what used to be bucket 3 is now bucket 2. So I need to make sure I'm checking bucket 2 the next time through. So I'll change 2 to 1, and then it becomes 2 again. So this makes sure that I check the same position in my linked list the next time around that I just removed, even though it's a new value. All right, because when I remove something from a linked list, that linked list is now smaller than it used to be. All right, this is being done in memory, so this will go through, and anything that's odd, I'll remove it, and then make sure that I'm still checking all the values by decrementing I, so I recheck that same position, but the new value the next time through. All right, assuming you have access to a linked list of ints, similar to what we wrote in class, write a method that takes a linked list as a parameter and duplicates the elements in the list. For example, access. Okay, so I guess I didn't necessarily, well, I'm not having you return it, so the presumption would be I am having you duplicate it in place. So we'll say void dupe LL. This guy will take a linked list pointer. LL is a parameter. Did I say pointer up here? I probably did, but I technically didn't. But I would not have taken off points for that. All right, so this guy is going to take a linked list pointer as a parameter. And what I want to do is I want to go through every element of the linked list for int I is equal to 0. I is less than LL get count I plus plus. All right. Now for each bucket of this guy, what I want to do is I want to duplicate it. So I'm going to say LL add at index I LL get at index I. So let's say I'm just dealing with bucket 0. I'm reading in the current bucket 0. I'm going to add in bucket 0 the current bucket 0, which then duplicates that value. But keep in mind, my linked list just got a little bit larger than it used to be. So just like in the last question, I then need to artificially inflate my linked list to be a little bit larger than, or inflate my counter to jump ahead. So the first time I'm doing bucket 0, well, after I do bucket 0, I now have bucket 0 and bucket 1 that are duplicates of each other. So my next time through, I need to make sure I get to a bucket 2. That's why I'm saying the I plus plus. All right, so I'm adding a new value at an index, one index I, and what am I adding? The current thing at bucket index I, so that'll give me 2 values, and then I'll jump ahead an extra value. So that'll inline duplicate the contents of my linked list. All right, assume there exists a linked list object that is capable of holding ints. You can make reasonable assumptions, blah, 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 blah. Write a recursive method, so it has to be recursive. Takes a stack and prints to the screen the contents of the stack. You don't have to preserve the stack. So I'm making this recursive. That was the thing. That's a function that calls itself from within itself. I am displaying stuff. Prints to the screen. So I'm displaying stuff to the screen. So it's going to return nothing. So we're going to call this guy print void. It's going to take a stack print pointer, pointer S. So I'll say if let's see, it's a stack. So we'll just say if s dot peak is not equal to null, if there's a thing at the top of the stack, then what do I want to do? I'll do a cout s pop, whatever the top of the stack is. I'll kick it down the line. I don't know why I said print void. This is print stack, probably the name of it. So then I'll call print stack with my updated s. S.pop will remove the top of the stack. Presumably it boils down to what you just removed. So I'm going to print out the value I just removed, but this right here will leave the stack one element shorter than it used to be. Then I'll go ahead and call print stack with that new version of the stack. This is my recursive call, which will come up here, and it's going to keep doing that as long as there's something at the top of the stack. As long as it gets to when it gets to the end, the very last time through, the stack is empty, so it won't do this, and we're done with the recursive calls. And like I said, you do not have to preserve the contents of the stack. So in this case here, I've destroyed my stack in memory because I just keep popping stuff off of it, but this will print out each element of the stack. And I'm doing this recursively. I'm going to keep calling this until I've emptied out the stack. Okay. Question 8. Assuming there exists a linked list object that are capable of holding ints, you can make result blah, 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 write a method named index of that takes and a linked list and an int for which to search. And okay, so we're writing index of. All right, so this guy's going to return an int. It's called index of. It's going to take a linked list pointer, LL, as a parameter. All right, and I'm searching for that guy in the linked list. So I'm going to go through potentially my entire linked list for I is equal to 0, I is less to LL, get count or size, whatever you want to call it. I think I tell you the functions up above. But something along those lines. I'm going to ask the question if LL get at index I is equal to, and this guy doesn't just take in a linked list, it takes in an int val as well, the thing I'm searching for. So if this guy is equal to the value I was looking for, then I'll go ahead and return the index where I found it. Remember, return makes a function immediately end. If I've gone through and I've searched the entire linked list and I never found the value, I'll return a -1. Works like the index of method in Java. So it returns the first occurrence of an element in a collection or -1 if it wasn't found. So loop through the contents of the entire linked list. For each element, ask, is this the dude I'm looking for? If it is, return its position. Otherwise, if I checked everything, return -1. Didn't find it. Question 9. Assume there exists a linked list object that are capable of holding ints. You can make reasonable assumption regarding the method, blah, blah, blah. Write a method named reverse list that takes a linked list as a parameter and returns a new linked list that is the original in reverse. All right, so I'm building a brand new linked list. This guy's going to return a linked list pointer. Call this guy reverse list. It'll take a linked list pointer as a parameter. All right, so I'll go ahead and I'm going to build my linked list pointer temp is equal to a new linked list. All right, so there's my new one, and I'm going to fill up this guy with my original linked list in reverse. So for it I is equal to the last legal bucket in LL is LL get count -1. Keep going as long as it's greater than or equal to 0. Subtract 1 each time. And what am I doing each time? I'm going to add it to the end. So add n to temp LL at index I. And return temp. Write an empty linked list. Walk my original one from end towards beginning. Add to the end of my new one. So we're always getting into the back line. So I'm building my new one as the reverse of my original one and not changing the original one. And then I'm returning the new linked list that I built as my answer here. Returns a new linked list that is the original in reverse. All right. You could have also done this by going through LL forwards and then adding to the front of temp, building it in reverse. Didn't matter. Logically, they both do the same thing. All right. Last question. Assume there exists blah, blah, blah. Write a method named removeatindex that takes a stack and a zero-based index as a parameter, and it should remove the element at that index in the stack, leaving the rest of the stack intact. Okay. So now this is updating a stack in memory. So we're not going to return anything. We're going to say remove at index, and this guy's going to take a stack pointer as a parameter. All right. And then we're going to go ahead and we will, we're going to need a temporary stack, because what we're going to do is as we peel things off the original stack to unearth the index that we want. Oh, and this guy needs to take in an index. I'm going to need to have a place to put those things. So I'm going to say a stack pointer temp is equal to a new stack like this. And then I'm going to say for int I is equal to 0, I is less than index, I plus plus. So I want to pop from my original stack and push onto my temp stack. So temp push S pop index number of times to reveal bucket index, 0-based index, at the top. Then I want to burn past that S pop. So that'll remove that element from my original stack. Now I want to go ahead and while temp peak is not equal to null. Okay, well, temp peak is not equal to null. So as long as I have stuff in my temp thing, I want to pop from temp, push back onto S, fill S back up with the stuff that I had previously popped off to reveal the element I was removing. So I'll say S push temp pop. And that'll keep happening as long as there's something at the end of temp. So at the end here, so reveal, that's what that loop does, reveals the element we want to remove, storing temporarily in this temp stack. Then this removes the element. Then this copies my temp stack back over onto my original stack in that original place in memory, which will leave my original stack with all the elements that was originally in it, except bucket index is now removed. Okay, so that should be the solution to the exam. All right, 27 minutes. And I said you had 50 minutes to take it. I was talking through it out loud. I might say it was slightly too long, maybe by a question. It wasn't difficult, but I could see that a couple of those questions needed additional thinking. So I'll take that into consideration when I'm grading it. I have not gotten them graded yet. I do apologize. I've been traveling, but I will get them graded as quickly as possible. But I did want you to see the solution before class started today, since I'm not going to be there, but I will see you on Friday. Okay. So that's the scoop, and I'll get this uploaded and I'll see everybody in class on Friday.